What was the other chapter this year, guys, as we start chapter 5? You're setting up the second page. I'll go back to the first page in 1 second. What was the other chapter this year that I brought up the idea of puzzles? That we had to learn, or games, that we had to learn the rules to before we could really play? Logarithms and exponentials. Weren't there a lot of rules with logarithms and exponentials? We had to learn how they behave, how they work, how we manipulate them, how we solve for x in them. Why didn't we spend a whole chapter on polynomials and how we combine them and multiply them and divide them and solve for x in them? Spent like a section, but why not a whole chapter on polynomials? How long have you been adding polynomials? A long time, right? Since algebra, pre-algebra. How long have you been subtracting polynomials? Just about as long. Combining like terms, degrees have to be the same. They have to, an x squared goes with an x squared. Just like apples go with apples and not oranges when you're counting things. I watched a seminar. No, not quite that. It was a TED Talk. There we go. And it was a math teacher up there being like, we could start teaching algebra to like kindergartners. It's like, I literally did. My 5-year-old niece at Christmas or something. He was like, I gave her all these different situations. Like, hey, I forget what the name is. Let's just call her Bailey because that's a cute name. If you have 5 apples, or like 1 apple and 1 apple, then the kid's pretty smart, but still. 1 apple and 1 apple, how many apples do you have if you put them together? 2 apples. Okay, if you have 2 oranges and 2 more oranges, how many oranges do you have? Like, he actually put them out and she counted them. 4 oranges, right? He kept on going with that. And he was like, well, what do you think if I have 1x and 1x? 2 x's. Like, it's not super hard, right? Just you don't really get introduced to it, sadly, in the American system until way later in school, like upper elementary, beginning of middle school. But you were working with x's and x squareds and all that jazz for a super, super, super long time. And yes, there were complicated things like multiplying, foiling, distributing, like dividing. Oop, that needs factoring. That's its own dilemma, right? There are tricky things with polynomials, but you've seen them for a long, 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 long time. How long have you worked with logarithms? Since middle school? No, you would have looked at your calculator and been like, what's a log, right? What's sin? What's cos? Anyway, sin on my calculator. So there's a lot of these things that you haven't seen as long. So naturally, you're not as familiar with them, which is why we spend time on them. We spend a whole chapter on trig, true? We spend a whole chapter on exponential logs, true? Okay. So now we're spending a whole other chapter on trig? Yeah, but in a different way. Introducing what is sine, what is cosine, what is tangent. We're not talking about the different ways you can see them in triangles and in angles of rotation and in word problems. We're not talking about going forwards and backwards with inverses. Last chapter was all the introductory stuff, the foundation upon which trig is formed, including their graphs of waves and then the cosines and the tangents. Oh, yeah. Don't worry, when you're in calculus, you can do that too. So, coming back. What's this page talking about? Well, hold on, pause. What was this page talking about? Basic formulas. And we saw them last chapter because they were basic. Now, which ones are harder than others? I kind of think these are trickier, right? Now, I want you guys to go ahead and, not to say they're not important, but can you guys put big old parentheses around these 2 categories? There's lots of donut holes too, guys, if you want to keep going. Put big old parentheses around the cofunction and the even odd. Put big old parentheses around the cofunction and the even odd. Not because they're not important, and you will need to use them in homework. They're just not as important as the first 3. So highlight the whole thing. It's all important, but put big old parentheses around the cofunction and the even odd. But this page is a reminder that we saw last chapter, if you remember, that even though these formulas are good, you can't just keep them static in your mind. Static? Static electricity, when my hair goes poof? No. What do I mean by static? Non-moving, non-changing. What's the opposite of static? Dynamic. Hey, what? You guys have actually learned something. Okay, but coming back, I don't want you to have all these formulas be static. I want you to realize they can move, they can change. Meaning, instead of just memorizing sine squared of something plus cosine squared of something, sine squared of blop plus cosine squared of blop, we call the blops u's or x's or thetas, equals 1. We can also say, well, based on that, then what can I say sine squared of x equals? Look at your properties. What can we say based on the Pythagorean? 1 minus. Yeah, we can rearrange. We can subtract cosine squared from both sides. And if there's an x in sine squared, there must be an x in cosine squared. So not only can the variables change, but also the arrangement can change. What can we say about cosine squared of x? 1 minus sine squared of x. Now, am I telling you to memorize all these? I don't know. Maybe for some of your brains. But for others, just realize, oh, hey, that with sine squared and cosine squared, I can move him around. As long as you legally move, algebraically move, subtracting or adding to both sides. What can you then say tangent squared of x is? Careful. Is it 1 minus? I think it's secant squared of x minus, right? Look at your formula. We have to move it legally. We can't just remember the pieces and put them in some random order. We have to say, oh, if this is the original, then to get tangent squared alone, I have to subtract 1. Does that make sense? So then what can I say cotangent squared of x is? But do you guys remember, is there another way? Could we, if we wanted to, which these are the main arrangements I wanted you guys to see, couldn't we technically make this something different? Couldn't I have tons of fun and do something like, whoo, now what am I doing? Not 1 over tangent squared of x. How did I do secant squared? Where'd that come from? Reciprocal. Look at the reciprocal identity. Isn't cosine 1 over secant? And do you guys remember that we can't get tricked by the trig notation? Whenever we see a trig, any trig, squared of x, it's the exact same thing as the trig of x squared. I know, it's really silly because there's no function called trig, but you guys know what I mean, right? Sine of x squared would be written sine squared of x, or tangent of x squared would be tangent squared of x. Don't get tricked by the trig notation. So I can actually take the squared out and say, whose cosine again? Oh, 1 over secant, and bring the squared back in for my notation. So what could I say is going on here with this guy? What could I say for this guy? What can I say for this guy? 1 over though, right? What can I say over here? Oh my goodness, can we go both ways? Couldn't I rewrite this guy to be 1 over cosecant squared? Couldn't I rewrite that guy to be 1 over sine squared? What could I rewrite tangent squared to be? 1 over cotangent squared, but what's a nicer one? I could also do sine squared over cosine squared. Because I can take the tangent, which is who's really inside when there's this notation, make him sine over cosine, and then square them both. What could I say this guy is? 1 over tangent squared, or cosine, ooh. I was saying one thing and I started writing it. Cosine squared over sine squared. So here's the dealio, guess what? If I had this, and I had that, we should be able to simplify it to be this. And this is the idea of, with all these different identities, the forms of equalities can change in crazy, crazy ways. The forms of things can change in crazy, crazy ways. Now, we saw in section 4.2, we saw them give us something like, oh, what would be a good example? How about something like, this is a really, really easy one, but tangent of x times cotangent of x is equal to 1. Do you remember that? And they gave you something like the directions. I told you guys, when they give you these directions, they're saying verify this is true. Verify this side equals that side. And then I said you have to go back to geometry and think about, just as far as making the format correct and getting ready for hard ones to come. If one side being a given and one side being a proof. But I also, you could actually make the given the right side and the proof the other side, because equations can be written either way. So we can actually make either one the given. But why do you think I made that the given? So I can work with it. I can't work with one. One could come from so many different places. From multiplication, from division, from subtraction, from, I don't know, square rooting, whatever. One can come from so many places. This, though, I'll go play with properties. And do you guys remember at least one way? There were a few different ways that we actually showed this to be true. You could change tangent to sine over cosine, and you could change cotangent to cosine over sine. In a way that anyone knows the basics of math, if you rewrite this as this, they're like, oh, of course that's 1 because that reduces, and we end up with 1. Hey, the given was able to be transformed to the proved. Dun, 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 dun. But what's different about what you see on the board than the problems that we saw in section 4.2? The basic. There's no equals. Okay, well, pause. Look at the directions. Are they saying verify? So they haven't given us the full two sides, the full given and prove. They've just given us, exactly. They've just given, right? They've just given us the givens. They haven't given us the proof. Guess where the proof is? In the back of the book. What? In section 5.2, they start giving you the givens and the proof. But the problems also get harder. Section 5.1 is just teaching you what you can do. For instance, if there was a verify, if this was the direction for all of section 5.2, it basically is. It's the direction for all of 5.2. Is it telling you how to verify? No. It's just saying verify. Do what you know how to do. Guess what 5.1 says? Let me teach you what to do, or what you can do. So look at these directions. One thing you can do when you're given trig identities. Factor and simplify. Oh, let's learn if we can do that. Let's see if we can do that with givens. Now, here's the tricky part. You don't know what you're trying to get to. You're just saying, okay, I'll do what you told me to. I guess I can do that. And that's why this chapter is called Analytic Trigonometry, because we're working analytically. Kind of think algebraically. We get to play with the trig and not just solve for it. So what do you guys see? Why would they tell you to factor? In calculus, we call it the green trick. It's looking at two nasty expressions separated by an addition or subtraction and saying, hey, is anything in common? Yeah. What's in common? Tan squared of x. And what's left when you factor? Wait, factoring is division, right? Dividing away. Foiling is multiplying. Dividing. What's left when you divide tan squared by tan squared? So if it helps, you could think of when you pull out the tan squared, you end up actually dividing everything inside by that tan squared. Now, I know a lot of you guys do this in your head, but there are just a few of you that never really realized what factoring was. You just got good at it, or maybe not so good at it. Whenever you factor, you're taking out the tan squared, and then you're dividing. You're actually multiplying by 1 creatively is what's really going on. But you end up with dividing by tan squared is 1, and dividing by tan squared gets you sine squared. Okay, we're done. We factored. No, the directions are telling you what you can do. You can factor, but what are the directions also telling you can do? How can I simplify? Ooh, didn't we just write him a second ago? What is 1 minus sine squared? Cosine squared. Oh my goodness, well that doesn't help anything. I mean, great, cosine squared. Why haven't I written tan squared down yet? Isn't tan squared sine squared over cosine squared? Oh my goodness, what happens? Technically reduced, but yes. They reduce. Reducing goes to 1, canceling goes to 0. Sine squared times 1 is sine squared. Oh my goodness, that huge beginning piece just becomes him? Oh, I could have done that. Tan squared minus tan squared is 0. And no, that's horribly illegal. Some of you are trying to make up math things in your head. The reason why this can become this is because of factoring and simplifying. Guess what you might need to use in 5.2 when the verify gets harder? Maybe factoring and simplifying. Every time? Nope. Sometimes? Yes. How does number 24 need factoring? Or how can we use factoring on number 24? The directions are helping you. You're just building the skills. You're not having the full puzzle yet. But how can we factor? Wait, this is easy. It's a 1 and it's a 2 and that goes away. All I have left is a squared. How illegal is that? So many kittens just died. So many kittens just died. I cannot reduce unless they match. Do they match? No, but what can I do? Why am I putting a plus and a minus? Difference of squares. Now, could I have also made cosine squared 1 minus sine squared? Technically, yeah. But is that following the directions of factor and simplify? No. See, they're guiding you in 5-1, being like, hint, hint, hint. Don't just go doing whatever you want to do. Tell you which direction to head. When you factor, life becomes so much nicer because now what do you see? A reduction that can be made. When you reduce, what's left? Careful, a 1 over, right? There you go. A 1 over. Simplify. I did. Make that 1 over secant, but something super nasty. It's a complex. Leave it. Yeah, it's the answer. Now, in section 5.1, I have given you a lot of odds. Do you know why? So you can know where to go. So some of you might do a factoring and might do a simplifying and be like, I think I'm done. Like in this example, this one's kind of basic. I don't know. Most of you hopefully wouldn't have gone any further. But do you see on this one, like some of you might have stopped right here and been like, what? I factored. Maybe you would have stopped here with tangent squared times cosine squared. What? I simplified. So look at the back of the book, not in the sense of like beating yourself up, oh my goodness, I can't believe I didn't get as far as they did. But more like, oh, I could have gone farther. Or, oh, I went illegally in this direction and it's not supposed to go there. Use the back of the book this time. Like seriously use it. Wait, use it to cheat? No. Use it to see if you've gone far enough, or if you've gone as far as you could go, or if you went far in the wrong way. Does that make sense? Okay. Now in section 5.2, once again, you'll see both sides. An illustration I used last year was a puzzle. The illustration I used last year was a puzzle. Question, you dump out all the puzzle pieces, and you say, let's go. Most people say, let's find the edges. Well, actually the corners first, right? The corners and all the edge pieces, like push all the other ones. We actually have like cookie sheets during Christmas, and we take all the other pieces off. We're like, get rid of them. Let's just get the edges. Okay, now let's start bringing in all the ones that seem to go in this quadrant, and in this part, and in this piece. Here's the snowman, here's the house, here's the sleigh, whatever. There's some sort of strategy to it, but all of it is going in the back of your mind, or having it propped up. Not just the edges and not just the inside pieces, but also what you're supposed to be getting. Doesn't the picture help? Well, what if someone gave you a puzzle and all the pieces were turned upside down and you didn't have a picture? Do you guys actually know there are puzzles out there that are just totally white? Don't know who would want to do that, but there is. That's, my aunt at Thanksgiving was like, yeah, it's a 1,000-piece puzzle, and there was no picture. I was like, oh, like not even on the pieces. There was no picture. Anyway, awful. But, I want you to think of section 5.1 as just how to put the pieces together. Like, oh, that piece fits. Oh, that piece doesn't fit. That's all section 5.1 is. It's just learning how the pieces fit. Learning what the different legal ways of putting together pieces are. Section 5.2 says, here's the full picture. So here you have the pieces, and here's what you want to get, make it work. Does that make sense? Okay, so use the back of the book in order to tell you what the picture is to give you an idea of where you're headed. Why is this guy a factoring problem? Why don't I just make him 1 minus sine squared? Well, number one, it says factor. And number two, what do you guys see? It's like a trinomial. Do you guys see it? Yeah. It's like a trinomial. But who's being squared? Cosine. Who's being... Oh, didn't we do this with... you guys remember this guy? This could have been in that section too. You don't just factor polynomials. You can also factor quadratic exponentials. And you can also factor, oh my goodness, quadratic trigonometric expressions. Now, question is, how's your factoring skills? What would you guys do? Take 36 off to the side and try to figure out what was going on to get 5? Maybe. I see a 9 and a 4. How about you guys? Oh, 9 and 4? But we could do 9 cosine and 4 cosine. And then what can we look for? No, this is called grouping, remember? We're looking for GCFs. Looking for GCFs. Now, I did see a really creative way of factoring the other day. I might bring that back one of these days, but not today because we need to get this done for tomorrow. So just doing what we've always done, you can pull out a 2 cosine x and you get 3 cosine x. No. I mixed that up, didn't I? Pull out a 3. You get a 2 cosine x plus 3. And can't I pull out a 2? Did I not put my 4? Silly me. Lo siento. There we go. I didn't put the negative by the 4. 9 minus 4 makes 5, not 9 plus 4. Then what? Kinda. What are my 2 factors? Some of you might have gotten there with guessing and checking instead. 3 times 2, 3 cosine times 2 cosine does make 6 cosine. 3 times 2 does make negative 6, or I should say 3 times negative 2. Oh no, we have to simplify. No, we don't. What'd they tell you? This is just teaching you the skill of, guess what? Something like that you can factor. Oh, why thank you very much. Mr. Book who's trying to teach me. Does that make sense? We're just building skills. What are the skills we're going to build? Ooh, this one doesn't say factor. Why? Because there's nothing in common. Oh. Should I be scared of betas? Nah, whatever. They're a Greek letter. They're a variable. Like theta, like x, like you, like me. Anyway. So what are they telling you? If you see something like this, just because you can't factor doesn't mean you're stuck. Should I make sine 1 over cosecant? Should I make cosine 1 over secant? But what can I do? If you see an expression with sines and cosines, a tangent can be written in terms of sine and cosine, right? And then maybe if they're written in similar terms, maybe I can do something. It says there should be a way to simplify with identities. You were behind me. Sorry, kiddo. Thank you. I'll see you soon. Can the sine and cosine reduce? No? Yeah? I mean, I guess I can do sine times sine is sine squared. If I have a fraction times a non-fraction, maybe I should make it one combined fraction? Now I have a fraction and a non-fraction. He's in denominator, he's in numerator. I can't pull out from top because he's not in the top, and I can't pull out from bottom because he's not in the bottom. I could make that 1 minus cosine squared, but even if I factor to be 1 minus cosine, 1 plus cosine, it wouldn't reduce. They're not telling me factoring, so I bet that's not going to help. P.S. If I were you, in a color pen, I would do something like writing for yourself the clue. Sometimes you need to get common denominators. If you have a fraction and a non-fraction, multiply, get it together to be 1. If you have a fraction and a non-fraction, adding, get it together to be 1 fraction. But how do you do that? What am I going to multiply them by? No, I need a denominator. Cosine. See how I'm using color coding to kind of point out what the trick is in this one? Help my brain later so I can know, oh, hey, this was what was unique or different. What do I get? Sine squared over cosine plus cosine squared over cosine. Oh, hey, common denominators. I get to make one big old fraction. Well, that's awful and horrendous. What did that do? Wait. Yeah. Is that the only? The rest of you guys just stared at me blankly. No one else saw sine squared plus cosine squared is? So I can jump down and say, oh, hey, guys, this is just secant. Dun, 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 dun. What? Yeah, who's 1 over cosine? Of course it's secant. Now, might some of you guys have stopped way back here? Well, hopefully not after this example in notes, because you're like, wait, fraction, non-fraction, I better do common denominators. But some of you might have stopped here. You would have looked in the back of the book and been like, oh, boy, I better keep going. Some of you might have stopped here and been like, ha-ha, now I'm done. It's all together, one fraction. Look in the back of the book. Oh, I better keep going. Ah, dun, 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 dun. Let's build some more skills. What was this one talking about? Simplifying. Yeah, okay. The directions didn't really help. Guess what would help? The clue of common denominators when you have a fraction and a non-fraction, and the clue that you can always change tangent to be more similar to the terms around him, either to sines and cosines or to maybe secants or cotangents. Oh, hey, look! Maybe they'll actually tell you sometimes what you're supposed to be doing. Wait, they're so similar, though. Can't we just put them together? Why not? They're not the same. Jason, go stand up. Sorry, buddy. Gotta sleep at night. Go stand up. Nope, go stand up. Your eyes were closed and your head was completely relaxed. That's called sleeping. Okay, so coming up. You can take your notes if you want, if you're taking them. Okay, can't combine because they're different denominators, right? Can't combine because they're different denominators, but what should I do? But what am I going to multiply by? Yeah, kind of. The other guy, is that okay? So this guy needs to be multiplied by that guy. This guy needs to be multiplied by the other guy. What happens when we multiply? Yeah. Do you guys see that we're going to have secant x minus 1 and secant x plus 1? Oh my goodness, it's a difference of squares down there. Why am I being very specific to put parentheses around this guy? Don't want to kill a seal, do we? So then I can go ahead and distribute my negative, at which point my secants cancel to 0. My negative 1's combine. Negative 1 minus 1 is negative 2. And my denominator I can follow to be secant squared minus 1. Oh, that's tangent squared. Oh my goodness, and you don't have to be done there, because what can I do with over tangent squared? I can technically rewrite this to be negative 2 times 1 over tangent squared. And guys, who's 1 over tangent squared? Cotangent squared. Some of you guys might have stopped there. Some of you might have stopped there. Some of you might not have even multiplied that. You're building your skills, being like, oh, I can keep going. Ooh, something nice might happen. More skills, please. Okay. Substitute. What? Okay, this is kind of preparing you for a different type of problem, but still, I guess we have to follow what they tell us, right? Substitute. Well, what's substitute? Well, he's the only guy we got, right? We know what x is, and there's an x in our equation, so okay, fine. Don't know why, but fine. Square root of 9 minus who squared? 3 cosine theta squared. How do we do that, though? Because they don't just say substitute, they also say simplify. So there must be something else that I can do. ideas? What's 3 cosine times 3 cosine? You can bring that squared into the cosine. You can bring the squared into the 9. Simplify, but I don't get... Wait, why is she doing a parenthesis? Ooh, I'm trying to show you what the answer is before I get there. So far, so good? Isn't that 3 square root of 9? It's 3. Oh, what's 1 minus cosine squared? Nobody, where are you? Sine squared. Oh, square root of a squared. That's right, they cancel. But remember, square root of a square, there's always technically an absolute value left. Dun, 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 dun. 1 minus cosine squared, sine squared, and square root of a square. This is one of those algebra facts from before that we have to keep on reteaching you because they didn't really hit it home very good. There should be an absolute value left. Oh my goodness. Hey guys, what's section 5.1 to tell you? You can go ahead and sit down, Jason. 5.1, is it showing you the whole picture? Nope. It's showing you just a few pieces and being like, can you make these fit the right way? Section 5.2 is going to say, oh, here's the picture, make it work. Section 5.1, what are you going to use to make sure you've gone far enough in a legal way? The back of the book. Bye, guys. See you later. Whose notes are these? Oh, Joyce Kim. Oh, thank you. No, you're good, bud. I forgot to give it to you yesterday for your test. Bye. Kyle O'Dowd. Oh, you haven't left yet. I thought you were walking out the door. I was going to catch you.